There's a shadow dancing behind our sun right now, hidden from our view by 93 million miles of blazing solar fire. A world that mirrors our own, spinning in perfect synchronization with Earth's orbit, forever locked on the opposite side of our star. What if I told you that everything you thought you knew about our solar system was incomplete? That there's been a cosmic game of hide and seek playing out for billions of years, and we've only been seeing half the board? Today, we're going to explore one of the most tantalizing possibilities in astronomy, a concept that has captivated scientists, sparked countless theories, and inspired generations of dreamers to look up at the night sky and wonder what else might be out there. We're talking about Earth's potential twin planet, a world that could be thriving with life, civilization, maybe even watching us right back, all while remaining completely invisible from our perspective. But before we dive deep into this cosmic mystery, I want you to think about something. Right now, as you're watching this, Earth is hurtling through space at 67,000 miles per hour. We're passengers on a blue marble rocketing around a nuclear furnace. And for all our satellites, telescopes, and space exploration, there's still a massive blind spot in our cosmic neighborhood. The far side of the sun represents the ultimate hidden territory, a place where an entire world could exist without us ever knowing. The concept isn't just science fiction fantasy. Throughout history, brilliant minds have seriously considered this possibility. The ancient Greeks had a name for it, Counter-Earth, a world they believed balanced the cosmos. Even today, with all our advanced technology, the question lingers in the minds of astronomers and theorists worldwide. What makes this idea so compelling isn't just the romantic notion of a twin world. It's the scientific plausibility that keeps researchers awake at night, calculating orbits and analyzing gravitational effects. Because here's the thing, if such a planet existed, it would have to follow very specific rules to remain hidden for so long. Picture this scenario. Imagine a planet roughly Earth's size, maybe even Earth's exact twin, positioned at what astronomers call the L3 Lagrange point. This is a gravitationally stable position directly opposite Earth on the other side of the Sunday. In this cosmic dance, our hypothetical twin would maintain its hidden position, always staying 180 degrees away from us as both worlds complete their yearly journey around our star. The mathematics alone are staggering. For this hidden world to remain perfectly concealed, its orbital period would need to match Earth's precisely. We're talking about a synchronization so perfect that even the slightest deviation would eventually expose the planet as it drifted out of alignment. The gravitational choreography required for such a setup represents one of the most elegant possibilities in celestial mechanics. But let's dig deeper into why this matters beyond just satisfying our cosmic curiosity. If Earth does have a hidden twin, the implications ripple through every field of science we know. Planetary formation theories would need complete revision. Our understanding of how solar systems develop would shift dramatically. The very way we search for life in the universe could change overnight. Think about the biological possibilities. If this twin world formed from the same stellar nursery as Earth, it could have similar conditions, similar chemistry, maybe even similar evolutionary pressures. We could be looking at a planet where life not only exists, but has had the same 4.5 billion years to develop that life on Earth has had. The creatures on this world might have solved problems we're still working on. They might have technologies we haven't dreamed of. They might even be wondering about us. The gravitational effects alone tell a fascinating story. Our solar system is like a cosmic clock, with each planet's gravity influencing the others in measurable ways. If a hidden twin existed, its gravitational signature would create tiny but detectable perturbations in the orbits of other planets, particularly Mars and Venus. These effects would be subtle, requiring incredibly precise measurements, but they would be there. Modern astronomers have been studying these gravitational whispers for decades. Every slight deviation in planetary motion gets cataloged, analyzed, and cross-referenced. The search for hidden mass in our solar system has led to the discovery of numerous asteroids, comets, and even dwarf planets. But the far side of the Sun remains largely unexplored territory. The technological challenges of detecting such a world are immense. Our most powerful telescopes point outward to distant galaxies, not inward toward the Sun's blinding glare. Space-based observatories that could potentially peer around our star's edges are limited by their positions and the overwhelming brightness of solar radiation. It's like trying to spot a candle flame while staring directly into a searchlight. Recent advances in space exploration have opened new possibilities for investigation. The Parker Solar Probe, launched in 2018, has been diving closer to the Sun than any previous mission. While its primary mission focuses on studying solar wind and magnetic fields, the data it collects could potentially reveal gravitational anomalies that might indicate the presence of a hidden planet. Similarly, the European Space Agency's Solar Orbiter mission has been providing unprecedented views of our star from different angles. As these spacecraft continue their missions, they're mapping the gravitational landscape around the Sun with increasing precision. Any large mass hiding in the L3 region would eventually reveal itself through its gravitational influence. The historical context adds another layer of intrigue to this mystery. Ancient civilizations across the globe developed sophisticated astronomical knowledge, tracking planetary movements with remarkable accuracy. Some scholars argue that certain mythologies and creation stories might contain encoded information about cosmic bodies that were once visible, but have since been lost to our view. The Maya, for instance, had incredibly precise calendars that accounted for planetary cycles spanning thousands of years. Their astronomical observations were so accurate that modern scientists still reference their calculations. Could ancient astronomers have detected evidence of a hidden world through long-term observational patterns that we've since forgotten? Archaeological evidence from various cultures suggests knowledge of celestial bodies that don't match our current understanding of the solar system. Stone circles, temple alignments, and ancient texts occasionally reference astronomical phenomena that seem to require knowledge of planetary positions we can't explain with our current model of the solar system. But let's return to the hard science. The physics of planetary formation in our solar system provide both support and challenges for the hidden twin theory. Computer simulations of early solar system development show that multiple Earth-sized planets could have formed in the habitable zone around our Sunday. Most models suggest that gravitational interactions would have eventually ejected or merged these worlds. But some scenarios allow for stable configurations where twin planets could coexist. The concept of planetary migration adds another dimension to this puzzle. We now know that planets don't necessarily form in their final positions. Jupiter, for instance, likely migrated inward toward the Sun before moving back outward to its current orbit. This grand tack hypothesis explains many features of our solar system's architecture. If Earth had a twin, it might have formed elsewhere and migrated to the L3 point through complex gravitational interactions with other planets. The implications for astrobiology are profound. If life exists on this hypothetical twin world, it might have evolved along completely different pathways than Earth life. Different atmospheric conditions, magnetic field strength, or surface composition could have led to biological innovations we can barely imagine. The study of such life forms could revolutionize our understanding of biology itself. Consider the possibility that this twin world developed intelligent life. A civilization that arose in parallel with human development would face unique challenges and opportunities. They would see different constellations in their night sky, experience slightly different solar radiation levels, and potentially develop technologies based on their unique environmental pressures. The communication possibilities are particularly intriguing. If such a civilization exists and has developed radio technology, they might have been trying to contact us for decades or centuries. Their signals, however, would have to travel around the Sun to reach us, a journey that could distort or weaken the transmission beyond recognition. Radio waves can be bent by the sun's gravitational field, a phenomenon called gravitational lensing. This effect could theoretically allow communication between Earth and its hidden twin, but the technical challenges would be enormous. The signals would need to be incredibly powerful and precisely aimed to account for the sun's interference. The energy requirements for such communication would be staggering. Any civilization attempting to send signals around the sun would need technology far beyond our current capabilities. This raises questions about whether we've been looking for extraterrestrial intelligence in the right places. Perhaps the most advanced alien civilization in our cosmic neighborhood has been hiding in plain sight, literally behind our backs. As we continue to develop more sophisticated detection methods and space exploration capabilities, the mystery of Earth's potential twin planet becomes more testable. Future missions to the outer solar system will provide new vantage points for observing the region behind the Sunday Advanced Gravitational Wave Detectors might pick up signatures of hidden massive objects. Even improvements in computer modeling could help us predict where to look and what to look for. The search continues, and with each passing year, our tools become more refined, our understanding deeper, and our ability to peer into the cosmic shadows more powerful. Whether Earth truly has a hidden twin or whether this remains a beautiful impossibility, the quest to answer this question drives us to explore, to question, and to never stop wondering what else might be out there, dancing in the darkness beyond our sight. The question of detection brings us to one of the most fascinating aspects of modern astronomy, the hunt for gravitational fingerprints. Every object in space leaves traces of its existence, invisible threads in the fabric of space-time that we're only just learning to read. If Earth's twin exists, it's been pulling on every piece of matter in our solar system for billions of years, creating patterns so subtle they're like whispers in a hurricane. But here's where things get really interesting. In 2019, a team of researchers at the Harvard-Smithsonian Center for Astrophysics published calculations showing that a planet hiding at the L3 point wouldn't remain perfectly concealed forever. The gravitational dance of our solar system is far more complex than a simple two-body problem. Jupiter's massive influence, the combined pull of all the outer planets, even the gentle tug of passing asteroids, would gradually nudge our hidden twin out of perfect alignment. Their models suggested that over geological timescales, spanning millions of years, such a planet would slowly drift into visibility. This creates a tantalizing possibility. Maybe Earth did have a twin in the distant past, and we're living in the era just after it wandered into view. Or perhaps we're approaching the moment when it will finally peek around the sun's edge for the first time in human history. The timing couldn't be more perfect for such a discovery. We're living through a golden age of exoplanet detection, with thousands of worlds beyond our solar system cataloged and analyzed. The techniques we've developed to find planets orbiting distant stars, methods like transit photometry and radial velocity measurements, could theoretically be adapted to search for hidden objects much closer to home. NASA's Transiting Exoplanet Survey Satellite, known as TESS, has revolutionized our ability to spot planets by the tiny shadows they cast when passing in front of their stars. While TESS focuses on distant systems, the same principles could guide future missions designed to monitor the edges of our sun for any unexpected transits or gravitational anomalies. The European Space Agency has proposed even more ambitious projects. Concepts for solar gravitational lensing missions would use our sun itself as a giant telescope, positioning spacecraft at specific points where the sun's gravity bends and focuses light from behind it. Such missions could potentially provide direct images of any objects lurking in the L3 region, finally settling the question once and for all. But let's explore an even more mind-bending possibility. What if the reason we haven't found Earth's twin isn't because it doesn't exist, but because it exists in a state we haven't considered? Recent discoveries in planetary science have revealed worlds that challenge our basic assumptions about what planets can be and how they behave. Take the concept of rogue planets, worlds that have been ejected from their home systems and now wander through interstellar space. Some researchers propose that Earth's twin might not be orbiting the Sun at all anymore. Instead, it could have been flung out of the solar system eons ago, now drifting through the cosmic void as a dark, frozen world carrying the fossilized remains of whatever life once thrived on its surface. The discovery of such a rogue Earth would be both tragic and profound. Imagine finding a world that once bloomed with oceans and continents, forests, and perhaps even civilizations, now locked in eternal winter as it tumbles through the darkness between stars. The scientific treasures buried in its frozen crust would represent the ultimate archaeological expedition, a chance to study a parallel evolution that took a dramatically different path. Advanced computer simulations of early solar system dynamics have revealed just how chaotic those first few 100 million years really were. The period astronomers call the Late Heavy Bombardment wasn't just a time of asteroid impacts. It was an era of planetary billiards, where worlds the size of Mars routinely collided, merged, and scattered. In such an environment, maintaining a stable twin-planet configuration would have been extraordinarily difficult. Yet, some models show it's not impossible. If Earth's twin formed with just the right mass, in just the right location, with just the right initial velocity, it could have survived the cosmic chaos of the early solar system. The key would have been achieving a resonant orbit, a gravitational harmony that protected it from the destabilizing influences of the giant planets. This resonance concept opens up another intriguing avenue of investigation. Throughout our solar system, we see examples of resonant relationships between celestial bodies. Pluto and Neptune maintain a 3-to-2 resonance, ensuring they never approach too closely despite their overlapping orbits. Many of Jupiter's moons dance in complex resonant patterns that have remained stable for billions of years. If Earth and its twin establish such a resonance, it would represent one of the most perfect examples of gravitational choreography in the known universe. The mathematical beauty of such an arrangement would be breathtaking. Two worlds locked in an eternal dance, forever hidden from each other, yet forever connected by invisible threads of gravity. The search for this cosmic twin has also led to unexpected discoveries closer to home. As astronomers have developed more sensitive instruments to look for hidden planets, they've found a treasure trove of previously unknown asteroids, comets, and small bodies throughout the solar system. Each new discovery adds another piece to the puzzle of how our cosmic neighborhood formed and evolved. Some of these objects show orbital characteristics that suggest they might have been influenced by a larger, undiscovered body. Certain asteroids follow paths that seem to require gravitational perturbations from something more massive than the known planets can provide. While these anomalies are subtle and could have other explanations, they keep the possibility of a hidden planet alive in the minds of researchers. The technological revolution in space exploration has also opened up new methods for investigation that would have been pure fantasy just decades ago. Swarms of tiny spacecraft, each no larger than a smartphone, could theoretically be launched toward the Sun's far side to conduct a comprehensive survey of the L3 region. These miniature explorers would face incredible challenges from solar radiation and heat, but advances in materials, science, and electronics are making such missions increasingly feasible. Artificial intelligence has become another powerful tool in the search. Machine learning algorithms can now process vast amounts of astronomical data, identifying patterns and anomalies that human researchers might miss. These AI systems have already discovered new exoplanets, predicted stellar behavior, and even helped design more efficient spacecraft trajectories. Turning such systems loose on the problem of finding Earth's twin could yield surprising results. The philosophical implications of discovering a twin Earth go far beyond science. Such a world would force us to confront fundamental questions about our place in the universe, the nature of life, and the meaning of uniqueness. Are we truly alone in our immediate cosmic neighborhood? Or have we been sharing our orbital path with siblings we never knew existed? If intelligent life developed on this hidden world, the cultural exchange possibilities are staggering to consider. Two civilizations that evolved in the same solar system, under the same sun, yet developed in complete isolation from each other. The differences in art, philosophy, technology, and social organization could provide insights into the fundamental nature of consciousness and creativity. The discovery would also reshape our understanding of planetary protection and cosmic responsibility. If life exists on Earth's twin, what obligations would we have toward preserving and protecting it? The ethical frameworks we've developed for terrestrial conservation would need to expand to encompass an entire additional world. As we stand on the threshold of this potential discovery, the excitement in the scientific community is palpable. New missions are being planned, new instruments are being designed, and new theories are being tested. The mystery of Earth's possible twin planet represents one of the last great unknowns in our immediate cosmic neighborhood, a puzzle that has captivated human imagination for millennia and may finally be within our grasp to solve. The hunt for gravitational anomalies has led us down some truly unexpected paths. In recent years, spacecraft missions have detected minute variations in the orbits of Mars and Venus that don't quite match our current models. These discrepancies are tiny, measured in fractions of seconds over decades of observation, but they're persistent. Something out there is tugging on our neighboring planets in ways we can't fully explain. The most intriguing of these anomalies comes from the orbit of Mars. Every 26 months, when Mars reaches opposition and aligns with Earth and the Sun, there's a slight deviation in its expected position. The deviation is so small that early astronomers dismissed it as measurement error. But as our instruments have become more precise, the pattern has become undeniable. Mars is being pulled ever so gently by something massive that we can't see. This gravitational whisper could be the smoking gun we've been looking for. If Earth's twin exists at the L3 point, its gravitational influence on Mars would create exactly this kind of subtle orbital perturbation. The mathematics work out beautifully. A planet with Earth's mass, positioned directly opposite us around the Sun, would create gravitational effects that match many of the unexplained variations we're seeing in Martian orbital data. But there's a catch that makes this mystery even more compelling. The strength of these gravitational anomalies suggests that whatever's causing them might be more massive than Earth. We could be looking at a super-Earth twin, a world perhaps 20 or 30% larger than our own planet. Such a world would have stronger gravity, potentially thicker atmospheres, and radically different evolutionary pressures for any life that might have developed there. The implications of a larger twin planet are staggering. If this world has Earth-like conditions but stronger gravity, life there would have evolved under very different constraints. Creatures would need to be more robust, more compact, better adapted to higher atmospheric pressures. Flying would be more difficult, but swimming might be easier in denser atmospheres. The entire evolutionary tree of life could have taken dramatically different branches. Recent advances in gravitational wave detection have opened yet another avenue for investigation. The LIGO and Virgo observatories, designed to detect ripples in spacetime from distant cosmic collisions, are becoming sensitive enough to potentially pick up gravitational signatures from large objects within our own solar system. A hidden super-Earth would create constant, low-frequency gravitational waves as it orbits the Sun, patterns that might be detectable with the next generation of even more sensitive instruments. The timing of our technological development couldn't be more fortuitous. We're entering an era where multiple independent methods for detecting hidden planets are converging. Gravitational analysis, advanced space missions, AI-powered data analysis, and gravitational wave detection are all reaching the sensitivity levels needed to finally solve this cosmic mystery. But let's consider an even more extraordinary possibility that's been gaining traction among theoretical physicists. What if Earth's twin isn't just hidden behind the Sun, but exists in a slightly different dimensional space? Recent theories in quantum mechanics and cosmology suggest that parallel realities might not be as separate as we once thought. There could be thin barriers between dimensions, places where objects from one reality occasionally influence another. This concept, while it sounds like pure science fiction, is grounded in legitimate physics. The many worlds interpretation of quantum mechanics proposes that every quantum event creates parallel universes. Some theoretical models suggest these parallel realities might occasionally interact through gravitational forces. If Earth's twin exists in a parallel dimension that's gravitationally connected to our own, it could explain why we detect its effects but can never see it directly. The dimensional twin theory would resolve many of the puzzles surrounding the hidden planet hypothesis. It would explain why the gravitational effects are detectable, but the planet itself remains invisible. It would account for why the orbital mechanics work mathematically, but observational confirmation has been so elusive. Most intriguingly, it would open up possibilities for communication and interaction that transcend our current understanding of physics. Imagine the technological implications if we could establish contact with a dimensional twin Earth. The civilizations there would have developed under identical stellar conditions but completely different evolutionary pressures. Their solutions to energy, transportation, communication, and survival might be radically different from ours. The exchange of knowledge between two Earths could accelerate human development by thousands of years. The search for dimensional signatures has become one of the most cutting-edge areas of modern physics. Particle accelerators are probing the fundamental structure of reality, looking for evidence of extra dimensions and parallel realities. Some experiments have detected anomalies that could be explained by gravitational leakage from parallel universes. While these results are still controversial and require much more verification, they hint at a cosmos far stranger and more interconnected than we ever imagined. Advanced computer simulations have also revealed something fascinating about planetary formation in systems like ours. The gravitational interactions between forming planets create what physicists call chaotic zones, regions where small differences in initial conditions lead to dramatically different outcomes. In some simulations, twin Earths form naturally and remain stable for billions of years. In others, they collide catastrophically or get ejected from the system entirely. The most stable twin planet configurations occur when both worlds develop at exactly the same distance from their star, locked in perfect gravitational resonance. This creates a cosmic seesaw effect where the gravitational pull of each planet balances the other, maintaining their hidden dance for geological timescales. The mathematical elegance of such systems has inspired some researchers to argue that twin planets might actually be more common in the universe than solitary worlds like we once thought Earth was. Recent observations of other star systems have provided tantalizing hints that twin planets might indeed exist elsewhere in the galaxy. The Kepler Space Telescope discovered several planetary systems where the gravitational dynamics strongly suggest the presence of unseen companion worlds. While we can't directly observe these hidden planets due to their distance, their gravitational signatures are unmistakable. One particularly intriguing system, located about 127 light-years from Earth, shows clear evidence of twin super-Earths orbiting their star in perfect opposition. The system's gravitational dynamics create periodic variations in the brightness of the host star, patterns that can only be explained by two massive planets pulling in opposite directions. If twin planets can exist in other star systems, there's no reason they couldn't exist in our own. The biological implications of discovering Earth's twin continue to evolve as we learn more about life's adaptability. Recent discoveries of extremophile organisms thriving in conditions once thought impossible have expanded our understanding of where life might exist. If Earth's twin has different atmospheric conditions, temperature ranges, or radiation levels, Life there might have evolved along pathways that seem alien to us but are perfectly adapted to their environment. Consider the possibility that Earth's twin developed a methane-based atmosphere instead of our oxygen-rich environment. Life there might breathe methane and exhale hydrogen, creating ecosystems based on completely different chemical cycles. Such organisms would be perfectly suited to their world, but would find Earth's atmosphere as toxic as we would find theirs. The discovery of such life would revolutionize astrobiology and force us to reconsider what we mean by habitable conditions. The magnetic field dynamics of a twin planet present another fascinating area of speculation. Earth's magnetic field is generated by the movement of molten iron in our planet's core, but the exact mechanisms are still not fully understood. A twin Earth with slightly different internal composition or rotation rate might have developed a completely different magnetic field structure. This could affect everything from atmospheric retention to radiation protection to the development of life itself. Some theoretical models suggest that twin planets in the same system might actually share magnetic field characteristics, creating interconnected magnetospheres that stretch across the space between them. Such a configuration could provide enhanced protection from cosmic radiation for both worlds, potentially making life more likely to survive and thrive on each planet. The search technologies continue to advance at an unprecedented pace. NASA's James Webb Space Telescope, while primarily designed to observe distant galaxies and exoplanets, has the sensitivity to potentially detect infrared signatures from objects within our solar system. If Earth's twin has different surface temperatures or atmospheric composition, it might emit infrared radiation in patterns that would be detectable even from behind the sunday. Private space companies are also joining the hunt with innovative approaches that government agencies might not consider. Some proposals involve launching networks of small, inexpensive satellites that could monitor the gravitational environment around the Sun continuously. Others suggest using advanced asteroid mining spacecraft as secondary observation platforms, taking advantage of their deep space trajectories to search for hidden objects from multiple angles. The cultural and philosophical preparations for such a discovery are already beginning. International space law would need to be completely revised to account for the possibility of a second-like world into Earth, our solar system. Questions of territorial claims, resource rights, and environmental protection would become incredibly complex if we suddenly found ourselves sharing our orbital neighborhood with another potentially habitable planet. Religious and philosophical communities are also grappling with the implications. The discovery of Earth's twin would challenge many fundamental assumptions about humanity's unique place in creation. It would force us to consider whether consciousness and intelligence are rare cosmic accidents or natural consequences of Earth-like conditions. The answers could reshape our understanding of purpose, meaning, and our responsibilities as the only known intelligent species in our solar system. As we stand on the brink of potentially answering one of humanity's oldest questions, the excitement is building across multiple fields of science and exploration. Whether Earth's twin exists as a physical world, a dimensional neighbor, or remains forever a beautiful impossibility, the search itself is pushing the boundaries of human knowledge and technological capability. The next decade promises to bring unprecedented advances in our ability to probe the hidden corners of our solar system. New missions are being planned, new instruments are being developed, and new theories are being tested. The cosmic game of hide-and-seek that has captivated our imagination for millennia may finally be approaching its conclusion. But perhaps the most remarkable aspect of this quest isn't the destination, but the journey itself. The search for Earth's twin has already led to countless discoveries, technological innovations, and expanded our understanding of planetary science, gravitational dynamics, and the possibilities for life in the universe. Whether we find our cosmic sibling or not, we've become better explorers, better scientists, and perhaps better humans in the process of looking. The search for our hidden twin has also revealed something unexpected about the nature of time itself. Einstein's theories tell us that gravity doesn't just bend space, it bends time too. A planet hiding behind the sun would exist in a slightly different gravitational environment than Earth, experiencing time at a marginally different rate. Over billions of years, this temporal drift could accumulate into measurable differences. This means that if Earth's twin exists, it might literally be living in a different moment than we are. Not dramatically different, perhaps only microseconds ahead or behind our timeline, but enough to create fascinating possibilities for understanding the relationship between gravity, time, and consciousness. If intelligent life developed there, their perception of temporal flow might be subtly but fundamentally different from ours. The quantum implications become even more intriguing when we consider recent breakthroughs in quantum entanglement research. Some theoretical physicists have proposed that planets forming from the same stellar material might maintain quantum connections across vast distances. If Earth and its twin condensed from the same protoplanetary disk, they could share entangled particles that would allow instantaneous information transfer between the two worlds, completely bypassing the communication delays imposed by the speed of light. This quantum connection theory has led to some fascinating experimental proposals. Researchers are developing increasingly sensitive quantum detectors that might be able to pick up entangled signatures from across the solar system. If such connections exist, they could provide a communication method that works around the sun's interference, finally allowing direct contact between Earth and its hidden sibling. But let's dig deeper into the atmospheric possibilities that have captivated climatologists worldwide. Computer models of twin planet atmospheres suggest that even small differences in initial conditions could lead to radically different weather patterns and climate systems. Earth's twin might have developed monsoon cycles that dwarf anything we experience, or perhaps ice ages that last for millions of years longer than our own. The atmospheric chemistry alone opens up worlds of possibility. If the twin planet formed with slightly different ratios of volcanic gases, its atmosphere might have evolved along completely different pathways. Instead of our nitrogen-oxygen mix, it might have developed a dense carbon dioxide atmosphere with floating continents of crystallized methane. Or perhaps it found a completely different atmospheric equilibrium, one that supports liquid water but through chemical processes we've never encountered. Recent discoveries of atmospheric rivers on Earth, massive streams of water vapor that flow through our atmosphere like aerial highways, have made scientists wonder what equivalent systems might exist on a twin world. With different gravitational conditions, rotation rates, or magnetic field strengths, these atmospheric currents could take forms that seem almost magical to our Earth-based understanding of weather. The magnetic field interactions between twin planets present another layer of mystery that's keeping plasma physicists awake at night. If both worlds have active magnetic fields, they would create a complex electromagnetic environment throughout their shared orbital space. Solar wind particles could bounce between the two magnetospheres, creating aurora displays visible from both planets and potentially affecting atmospheric chemistry in ways we're only beginning to understand. Some models suggest that twin magnetic fields could create stable channels of charged particles that flow between the two worlds. These electromagnetic highways might affect everything from cosmic ray exposure to radio communication, creating a shared magnetic environment that influences both planets simultaneously. The northern lights on Earth's twin might dance to rhythms set by our own magnetic field fluctuations. The geological implications are equally fascinating. Tidal forces between twin planets would be incredibly complex, potentially creating unique patterns of volcanic activity, earthquake cycles, and mountain formation. The gravitational pull between two Earth-sized worlds sharing the same orbit could generate internal heating through tidal flexing, keeping both planets geologically active for billions of years longer than solitary worlds. This enhanced geological activity might actually be beneficial for life. The constant recycling of crustal materials would ensure that essential elements remain available at the surface. Volcanic outgassing could maintain atmospheric composition over cosmic timescales. The tidal heating might even prevent the complete freezing of subsurface oceans during ice ages, providing refuges where life could survive even the most extreme climate changes. The implications for astrobiology extend beyond just the presence of life to questions about its development and intelligence. Two worlds sharing the same stellar environment but evolving in isolation would represent the ultimate controlled experiment in biological development. Any differences in the life forms that evolved would provide unprecedented insights into the role of chance versus necessity in evolution. Consider the possibility that both worlds developed intelligent species, but at different rates or along different pathways. Earth's twin might be home to a civilization that achieved spaceflight millions of years before humans appeared. Or conversely, intelligent life there might just be beginning to emerge as we reach technological maturity. The timing possibilities create scenarios that range from poignant to thrilling. If the twin civilization is more advanced, they might have been observing us for millennia, watching our development with the same fascination that we study other species. They might have ethical codes that prevent interference with developing civilizations, explaining why we've never detected their presence. Or perhaps they've been trying to communicate with us for generations, using methods so advanced that we haven't recognized their attempts as artificial signals. The reverse scenario is equally compelling. If we discover a twin world where intelligent life is just beginning to emerge, we would face unprecedented ethical dilemmas about contact, observation, and protection. Would we have a responsibility to help guide their development? Or would any interference represent a form of cosmic imperialism? These questions would challenge every assumption we have about our role in the universe. The technological exchange possibilities between twin civilizations capture the imagination of engineers and inventors worldwide. Two worlds developing under identical stellar conditions but complete isolation would likely solve technological challenges in completely different ways. Their approaches to energy generation, transportation, communication, and material science might be so different from ours that they seem like magic. Imagine spacecraft that use gravitational manipulation instead of chemical rockets, or communication systems that work through quantum entanglement rather than electromagnetic radiation. A twin civilization might have developed biotechnology that integrates living organisms into their machines. Or perhaps they discovered ways to harness dark energy for practical applications. The knowledge exchange between two isolated but equally advanced civilizations could accelerate technological development beyond our wildest projections. The energy dynamics of a twin planet system create fascinating possibilities for resource sharing and cooperation. If both worlds develop advanced space travel capabilities, they could establish permanent bases at the gravitationally stable Lagrange points between their orbits. These space stations could serve as meeting points for cultural and scientific exchange, neutral territories where both civilizations could work together on projects that benefit both worlds. Solar energy collection becomes particularly interesting in a twin planet scenario. Arrays of solar collectors positioned at the Lagrange points could gather energy from all angles around the Sun, feeding power to both worlds through microwave transmission or other advanced power distribution systems. The combined energy infrastructure of twin civilizations could dwarf anything either world could achieve alone. The search methodologies continue to evolve as our understanding of gravitational dynamics improves. New mathematical models that account for the complex interactions between all solar system bodies are revealing subtle patterns that might indicate hidden mass. These models require supercomputers running calculations for months at a time, but they're uncovering gravitational signatures that were previously invisible. Machine learning algorithms trained on these vast datasets are beginning to identify patterns that human researchers might never notice. These AI systems can process millions of orbital calculations simultaneously, looking for the tiny deviations that would indicate gravitational influence from an unknown source. As these algorithms become more sophisticated, They're developing an almost intuitive sense for the gravitational rhythms of our solar system. The space archaeology potential of finding Earth's twin extends beyond just discovering life to uncovering the deep history of our solar system. If the twin world preserves different geological records than Earth, it could provide missing pieces of the puzzle about how our cosmic neighborhood formed and evolved. Impact craters, volcanic formations, and sedimentary layers could tell stories about events that Earth's own geological processes have long since erased. Even if the twin planet is completely lifeless, it would represent an invaluable laboratory for understanding planetary development. We could study how Earth-like worlds evolve when subjected to slightly different conditions, providing insights that would help us understand both our own planet's future and the potential for life around other stars. The philosophical implications continue to deepen as we consider what finding a twin Earth would mean for human identity and purpose. Are we truly unique? Or are we part of a broader pattern of consciousness that emerges naturally under certain conditions? The discovery would force us to confront fundamental questions about what makes us special and what responsibilities come with intelligence in a cosmos that might be far more populated than we ever imagined. Religious and spiritual communities worldwide are already grappling with these possibilities. Some see the potential discovery as confirmation of divine abundance, evidence that creation is far richer and more complex than traditional teaching suggested. Others worry about the implications for human significance in a universe that might contain multiple versions of our own world. The scientific preparation for such a discovery involves more than just building better telescopes and space probes. Researchers are developing new frameworks for understanding planetary systems, biological development, and the emergence of intelligence. These theoretical foundations will be crucial for interpreting whatever we might find hiding in the shadows behind our Sunday. International cooperation has become essential as the search intensifies. No single nation has the resources or expertise to tackle such a monumental investigation alone. Collaborative projects involving space agencies, universities, and private organizations from around the world are pooling their knowledge and capabilities to solve this cosmic mystery. The economic implications of discovering Earth's twin could reshape entire industries. Space exploration would receive unprecedented funding and support as governments and private investors recognize the potential for expansion into a confirmed Earth-like environment. Technologies developed for twin planet exploration could revolutionize everything from materials, science, to energy production, to communication systems. But perhaps most importantly, the search itself continues to inspire new generations of scientists, engineers, and explorers. The possibility that we might not be alone in our immediate cosmic neighborhood has captured imaginations worldwide, motivating students to pursue careers in astronomy, physics, and space exploration. Whether we find our twin or not, the quest is already ensuring that humanity's future will be filled with curious minds ready to tackle the next great cosmic mystery. The hunt for Earth's hidden twin represents more than just scientific curiosity. It embodies humanity's deepest drive to explore, to question, and to reach beyond the boundaries of the known world. As our instruments become more sensitive and our theories more sophisticated, we're approaching the moment when this ancient question might finally receive its answer. The shadow dancing behind our sun may soon step into the light, revealing secrets that could transform our understanding of life, intelligence, and our place in the grand cosmic story that continues to unfold around us. The detection technologies being developed for this cosmic hunt are pushing the boundaries of what we thought possible just a decade ago. Scientists at the European Southern Observatory have been working on a revolutionary concept called interferometric imaging, where multiple space-based telescopes work together as a single, massive instrument. By positioning these telescopes at strategic points around our solar system, they could theoretically peer around the sun's edge with unprecedented clarity. This distributed telescope network would function like a cosmic microscope, using the gravitational lensing effect of the sun itself to magnify and focus light from the hidden region. The technical challenges are staggering, requiring precise positioning of spacecraft millions of miles apart and synchronizing their observations to within nanoseconds. But the potential payoff could finally give us direct visual confirmation of what's lurking in Earth's cosmic shadow. Private space ventures have also entered the race with increasingly bold proposals. One particularly ambitious project involves launching a constellation of tiny probes, each no larger than a coffee cup, on trajectories that would loop around the sun's poles. These miniature explorers would be equipped with advanced sensors capable of detecting gravitational anomalies, magnetic field disturbances, and even faint infrared signatures that might betray the presence of a hidden world. The beauty of this swarm approach lies in its redundancy and coverage. Where a single large spacecraft might fail or provide limited data, dozens of small probes could create a comprehensive map of the gravitational environment behind the sunday. Each probe would communicate with its neighbors, creating a real-time network of sensors that could track even the subtlest changes in the cosmic landscape. Recent breakthroughs in quantum sensing have opened yet another avenue for detection. Quantum gravimeters, devices so sensitive they can measure gravitational changes smaller than those caused by a person walking past the instrument, are being adapted for space-based applications. These instruments could potentially detect the gravitational signature of Earth's twin from hundreds of millions of miles away, picking up the cosmic whispers that traditional instruments might miss entirely. The quantum approach represents a fundamental shift in how we think about detection. Instead of looking for light or radio waves, quantum gravimeters would sense the actual curvature of space-time caused by hidden mass. This method could work regardless of whether the twin planet has an atmosphere, magnetic field, or any other detectable characteristics. Pure mass alone would be enough to reveal its presence through the subtle warping of space itself. But let's explore one of the most intriguing aspects of this mystery: the possibility that we've already detected Earth's twin without realizing it. Deep in the archives of astronomical data collected over the past century, there might be signals, patterns, or anomalies that only make sense in the context of a hidden planet. Researchers are now applying artificial intelligence to decades of observations, looking for correlations that human analysts might have dismissed as noise or measurement error. Machine learning algorithms trained specifically to recognize gravitational patterns have begun identifying subtle periodicities in planetary motion data that align perfectly with the orbital period of a hidden Earth mass object. These patterns are so faint that they require statistical analysis of thousands of observations to become apparent, but their consistency across different datasets is becoming increasingly difficult to ignore. The historical implications add another layer of fascination to this quest. If Earth's twin has been influencing our solar system's dynamics for billions of years, its effects might be embedded in the geological record of every planet. Impact patterns on the Moon, the timing of asteroid bombardments, even the long-term climate cycles of Mars could all carry signatures of gravitational perturbations from our hidden sibling. Paleoclimatologists studying Earth's ancient climate records have identified mysterious periodicities that don't correspond to any known astronomical cycles. These climate oscillations, spanning hundreds of thousands of years, might be influenced by the complex gravitational dance between Earth and its twin. If true, our planet's entire climatic history has been shaped by the invisible presence of our cosmic companion. The biological implications of these long-term gravitational influences extend far beyond simple climate effects. Evolution itself might have been guided by the subtle rhythms created by twin planet dynamics. Mass extinction events, evolutionary radiations, and the timing of major biological innovations could all be connected to gravitational cycles that we're only now beginning to understand. Consider the possibility that the emergence of complex life, the development of intelligence, and even the timing of human civilization have all been influenced by gravitational forces from our hidden twin. This would suggest that life on Earth isn't just the product of local conditions, but part of a larger cosmic symphony orchestrated by the gravitational interplay of twin worlds. The search has also revealed unexpected connections between seemingly unrelated phenomena. Solar activity cycles, the behavior of comets, and even the distribution of asteroids in our solar system all show subtle patterns that could be explained by the gravitational influence of a hidden planet. These correlations are painting a picture of a solar system far more interconnected and dynamically complex than we previously imagined. Recent analysis of comet trajectories has been particularly revealing. Comets entering our inner solar system from the distant Oort cloud sometimes follow paths that seem to require gravitational deflection from an unknown source. While these deflections could be caused by undiscovered asteroids or small planets, the most elegant explanation involves a single Earth mass object positioned exactly where our twin planet should be. The magnetic field dynamics between twin planets continue to yield surprising theoretical predictions. Computer simulations suggest that two Earth-like magnetic fields in the same orbital system would create stable magnetic corridors stretching across space. These electromagnetic highways could channel charged particles in complex patterns, potentially creating visible phenomena that we might have been observing for years without understanding their true origin. Some researchers propose that certain unexplained astronomical observations, from unusual aurora patterns to mysterious radio bursts, might actually be signatures of these twin magnetic field interactions. If true, we might have been watching evidence of our cosmic sibling for decades, misinterpreting the signals as unrelated phenomena simply because we weren't looking for connections. The energy implications of twin planet magnetic coupling are staggering to contemplate. If both worlds maintain active magnetic dynamos, the electromagnetic interaction between them could generate immense amounts of energy. This energy might manifest as unusual heating patterns in the upper atmospheres of both planets, or even as exotic forms of electromagnetic radiation that we're only beginning to detect. Advanced plasma physics models suggest that twin magnetic fields could create stable energy storage systems in the space between the planets. These natural electromagnetic batteries could accumulate solar wind energy over long periods, occasionally releasing it in spectacular displays that might be visible from either world. The northern lights on Earth could be synchronized with similar displays on our hidden twin, creating a cosmic light show that spans the solar system. The technological possibilities for harnessing these magnetic interactions capture the imagination of engineers worldwide. If we could understand and manipulate the electromagnetic connection between twin planets, we might be able to create communication systems that work instantaneously across vast distances, or even develop new forms of space propulsion based on magnetic field dynamics. The biological effects of twin magnetic field interactions present equally fascinating possibilities. Life on both worlds would have evolved under the influence of these complex electromagnetic environments. The navigation systems of migratory animals, the behavior of bacteria in magnetic fields, and even the development of consciousness itself might all be shaped by electromagnetic forces that exist nowhere else in the known universe. Recent discoveries about the role of magnetic fields in biological processes have revealed just how intimately life is connected to electromagnetic phenomena. If Earth's twin generates different magnetic field patterns, life there might have evolved completely different mechanisms for navigation, metabolism, and neural function. The study of such organisms could revolutionize our understanding of the relationship between electromagnetism and biology. The atmospheric dynamics of twin planets locked in electromagnetic embrace could create weather patterns unlike anything we see on solitary worlds. Charged particles flowing between the magnetospheres might seed cloud formation, influence storm development, or even create stable atmospheric rivers that stretch across interplanetary space. The climate on each world would be intimately connected to the magnetic activity of its twin. Theoretical meteorologists have proposed that twin planet atmospheres might even exchange material directly through magnetic field interactions. High-energy particles accelerated by electromagnetic forces could strip atmospheric molecules from one world and deposit them on the other. Over geological timescales, this exchange could lead to atmospheric compositions that reflect the combined evolution of both planets. The geological consequences of electromagnetic coupling between twin worlds open up entirely new categories of planetary science. Magnetic forces acting on iron-rich materials in planetary crusts could influence tectonic activity, volcanic patterns, and even the formation of mineral deposits. Both worlds might bear geological signatures of their electromagnetic relationship, written in the very rocks beneath their surfaces. These magnetic interactions could explain some of the mysterious features we see in Earth's own geological record. Certain magnetic anomalies in ancient rocks, unexplained patterns of mineral formation, and even the timing of magnetic pole reversals might all be connected to electromagnetic influences from our hidden cosmic twin. The search technologies continue advancing at breakneck pace, with new detection methods being proposed almost monthly. Gravitational wave observatories, originally designed to detect collisions between black holes, are being modified to search for the subtle space-time ripples that large planets create as they orbit. These instruments might be sensitive enough to detect the gravitational signature of Earth's twin directly, without requiring any visible light or electromagnetic emissions. Advanced computer simulations running on quantum computers are modeling solar system dynamics with unprecedented precision. These simulations can account for millions of variables simultaneously, tracking the gravitational effects of every known object while searching for patterns that might indicate hidden mass. As quantum computing power continues to expand, these simulations are approaching the accuracy needed to definitively confirm or rule out the presence of Earth's twin. The international collaboration required for such an ambitious search has led to unprecedented cooperation between space agencies, universities, and private organizations worldwide. The search for Earth's twin has become a unifying project that transcends national boundaries and political differences, bringing together the best minds from every continent in pursuit of one of science's most tantalizing mysteries. Educational institutions around the world are incorporating the search into their curricula, inspiring new generations of students to pursue careers in astronomy, physics, and space exploration. The possibility that we might discover a second Earth in our lifetime has captured imaginations in ways that few scientific endeavors ever achieve, creating a global community of citizen scientists eager to contribute to the hunt. The economic ramifications of such a discovery would reshape entire industries overnight. Space exploration companies would receive unprecedented investment as the prospect of reaching an Earth-like world becomes not just possible, but imperative. Technologies developed for twin planet exploration would find applications in everything from deep-sea exploration to materials science, driving innovation across multiple sectors. But perhaps the most profound impact would be psychological and philosophical. The confirmation that Earth is not unique, that we share our orbital neighborhood with another world capable of supporting life, would fundamentally alter humanity's perception of its place in the cosmos. We would no longer be alone in our immediate cosmic environment, but part of a binary system that has been dancing together since the dawn of the solar system. The discovery would force us to reconsider every assumption we have about planetary formation, biological evolution, and the development of intelligence. If two Earth-like worlds can exist in the same stellar system, the universe might be far more hospitable to life than we ever dared hope. The implications would ripple through every field of science, from biology to physics to philosophy. As we stand on the threshold of potentially answering this cosmic question, the excitement within the scientific community is reaching fever pitch. New missions are being planned, revolutionary instruments are being developed, and theoretical frameworks are being constructed to help us understand whatever we might find hiding in the shadows behind our Sunday The search for Earth's twin represents more than just scientific curiosity. It embodies humanity's deepest need to understand our place in the universe, to know whether we are truly alone or part of something larger and more wondrous than we ever imagined. Whether our cosmic sibling exists as a vibrant, living world or remains forever a beautiful dream, the quest to find it continues to push us toward new frontiers of knowledge and exploration. Every day brings us closer to the moment when this ancient mystery might finally be solved. Advanced telescopes are scanning the cosmos with unprecedented sensitivity. Space probes are diving deeper into the solar system than ever before, and our theoretical understanding of planetary dynamics continues to evolve. The shadow behind our sun may soon yield its secrets, revealing truths that could transform our understanding of life, intelligence, and our cosmic destiny. The journey of discovery continues, driven by the same curiosity that has always compelled humans to look beyond the horizon and wonder what lies hidden in the darkness. Whether Earth's twin exists or not, the search itself has already expanded our knowledge, enhanced our capabilities, and reminded us that the universe still holds mysteries waiting to be unveiled by those brave enough to seek them out. The discovery timeline we're facing couldn't be more thrilling. Within the next decade, multiple space missions will converge on the L3 region with unprecedented precision. The Parker Solar Probe's extended mission profile includes trajectory adjustments that will bring it closer to the gravitational sweet spot where our twin might be hiding. Meanwhile, the upcoming Interstellar Probe mission, scheduled for the late 2022, will provide the first direct observations of the space behind our sun from an entirely new perspective. These missions aren't just flying blind into the cosmic unknown. They're guided by increasingly sophisticated gravitational models that predict exactly where to look and what signatures to expect. If Earth's twin exists, these probes will detect its gravitational fingerprint long before they ever see it directly. The mathematics of orbital mechanics leave no room for such a massive object to remain hidden once we position our instruments correctly. But the search has also uncovered something unexpected about our own planet's behavior. Deep analysis of Earth's orbital data reveals tiny variations that occur in perfect synchronization with what a hidden twin's gravitational influence would create. These variations are so subtle that they were dismissed as measurement noise for decades, but advanced statistical analysis has revealed their underlying pattern with startling clarity. The synchronization is almost too perfect to be coincidental. Every 365.25 days, Earth's orbit shows microscopic deviations that align precisely with the gravitational pulls we'd expect from a twin planet. The timing, magnitude, and direction of these orbital adjustments create a signature that's becoming increasingly difficult to explain through any other mechanism. Recent breakthroughs in space-based interferometry have also opened up revolutionary detection possibilities. By linking multiple spacecraft positioned at different points around the solar system, astronomers can create virtual telescopes with baselines spanning hundreds of millions of miles. These distributed observatory networks could theoretically resolve objects as small as cities on Earth's twin, if such a world exists, and if we can position our instruments with sufficient precision. The technological challenges are immense, but the potential rewards justify every effort. Imagine the moment when we finally receive the first image of our cosmic sibling, a blue marble hanging in the darkness on the far side of our Sunday. The psychological impact would be immediate and profound, fundamentally altering humanity's sense of cosmic solitude in ways we're only beginning to understand. The atmospheric modeling studies have revealed another tantalizing possibility that keeps climate scientists awake at night. If Earth's twin developed along slightly different evolutionary pathways, it might have solved atmospheric problems that we're still struggling with. Their approach to greenhouse gas regulation, weather pattern management, or atmospheric composition could provide blueprints for addressing Earth's own environmental challenges. This isn't just idle speculation. Computer models of twin planet atmospheres consistently show that small differences in initial conditions can lead to dramatically superior environmental outcomes. A planet with Earth's basic characteristics but different volcanic activity patterns, ocean current configurations, or biological feedback loops might have achieved atmospheric stability that far surpasses our own world's delicate balance. The implications for climate science are staggering. If we could study how Earth's twin maintains atmospheric equilibrium, we might discover natural mechanisms for carbon sequestration, temperature regulation, or weather modification that could be applied to our own planet. The twin world could serve as a vast natural laboratory for testing environmental theories and developing solutions to problems that threaten our civilization's future. Recent advances in atmospheric analysis through gravitational microlensing have also created new possibilities for remote sensing. When light from distant stars passes near the L3 region, any atmosphere present on a hidden planet would create subtle but detectable distortions in the stellar spectra. These distortions could reveal not just the presence of an atmosphere, but its composition, density, and chemical activity. Several research teams are now conducting systematic searches for these microlensing signatures, monitoring thousands of background stars for the telltale spectral changes that would indicate atmospheric interference. The method requires incredible patience and precision, but it offers the possibility of analyzing Earth's twin atmosphere from 93 million miles away without ever seeing the planet directly. The biological signatures we might detect through such remote sensing open up possibilities that border on science fiction. If life exists on Earth's twin, its metabolic processes would leave chemical fingerprints in the planet's atmosphere. Oxygen, methane, water vapor, and other biological byproducts would create spectral lines that could be detected and analyzed using the same techniques we're developing to study exoplanets around distant stars. But here's where things get really interesting. If intelligent life exists on our cosmic twin, their industrial activities might also be detectable through atmospheric analysis. Pollution signatures, artificial greenhouse gases, or even the chemical byproducts of advanced manufacturing could create atmospheric anomalies that would be visible to sufficiently sensitive instruments. The possibility of detecting industrial civilization on Earth's twin through atmospheric chemistry represents one of the most exciting frontiers in the search for extraterrestrial intelligence. We might not need to wait for radio signals or visible light communications. The very air that hypothetical beings breathe could carry evidence of their existence across the vast emptiness of space. Current spectroscopic technology is approaching the sensitivity levels needed for such detections. The next generation of space-based spectrometers, designed primarily for exoplanet research, could theoretically identify industrial pollutants in Earth's twin atmosphere if they exist in sufficient concentrations. The irony is profound. We might discover our cosmic neighbors through their environmental impact, rather than their attempts to communicate. The quantum entanglement theories have also evolved in fascinating directions as our understanding of particle physics advances. Some researchers now propose that the quantum connections between twin planets might extend beyond simple information transfer to include more exotic phenomena like shared consciousness or distributed intelligence networks. These ideas venture into territory that challenges our fundamental assumptions about the nature of mind and awareness. If quantum entanglement can link particles across vast distances instantaneously, could it also create connections between biological systems? Might the consciousness that emerged on Earth be somehow linked to awareness developing on our twin world? The implications are both thrilling and unsettling. If minds on both worlds are quantum entangled at some fundamental level, the discovery of our twin might not just reveal another planet, but unlock new understanding of consciousness itself. We might find that intelligence isn't isolated to individual worlds, but part of a larger cosmic network that spans the solar system. Recent experiments in quantum biology have shown that quantum effects play crucial roles in photosynthesis, bird navigation, and even human cognition. If these quantum biological processes are sensitive enough to detect entanglement across interplanetary distances, the connection between twin worlds might manifest in ways we're only beginning to imagine. So here we stand, perched on the edge of the greatest revelation in human history. The shadow that's been dancing behind our sun for billions of years may soon step into the light, carrying with it answers to questions we've whispered to the stars since we first looked up and wondered if we were alone. Whether that shadow holds a twin world teeming with life, an empty rock drifting in cosmic silence, or remains forever just beyond our reach, the search itself has already transformed us. We've become better explorers, deeper thinkers, and perhaps most importantly, we've learned that the universe still holds mysteries grand enough to capture our collective imagination. The next time you see the sun setting on the horizon, remember that somewhere behind that blazing star, secrets are waiting. And maybe, just maybe, someone else is watching their own sunset, wondering about us too.